We're going to look at bisectors of triangles, two types. We're going to look at perpendicular bisectors of the sides of a triangle and then bisectors of the angles. But first, the sides. Now, I've got three triangles here. Let's look at this first one. Okay, now I'm going to take each side of this first triangle here and draw a perpendicular bisector. Okay, so and I'm just going to kind of eyeball it, but it looks like this is where the first perpendicular bisector would be. Notice it's 1, 2, 3 over, and then 1, 2, 3 here. So it looks like I've got the center. So it looks like I've bisected this first side here. Now I come to the next side, and I try to do the same thing, kind of eyeball it, trying to do a perpendicular. And that looks like about the center. In other words, I'm trying to get these sides, this side and this side of the bisector to be equal. So maybe I'll move it up a little bit, just a little, okay. Then I come over to the last side, and I want to do the same thing. I want to get the perpendicular bisector. So something like that, okay. Okay, now, so there we have the perpendicular bisectors. And now this is not exact because I was just eyeballing it. But notice that there is a point of intersection here, okay, inside the triangle. Now, just some terminology here. Whenever you have three lines that intersect at a point, we say that those lines are concurrent. And the point where they intersect, we call that the point of concurrency. Yeah, so you can see we have the point of concurrency right here. And in this triangle, you have the point of concurrency right here in the interior. Now, I have three types of triangles here. I have an acute triangle. Here I have a right triangle, and here I have an obtuse triangle. Now remember, the acute triangle, all the angles are less than 90. Of course, the right triangle, you have one of the angles is 90, and then the obtuse, one of the angles is bigger than 90. So if you look at these points of concurrency for each of these, for the right triangle, what you're going to have is you're going to have a point of concurrency right there on one of the sides. It would look something like this. Let me go ahead and see if I can kind of estimate here. Here's 1, 2, 3, 4, 5, 6. So maybe about right here. Whoops. There we go. Yeah. And then we have another one over here. And then we have this one. Let's see here. 1, 2, 3, 4. So there we go. There. And you notice that the point of concurrency is right there on this, on the side of the triangle. Now, if we do the same thing for this obtuse one, let's see what we get over with this one. We've got 1, 2, 3, 4, 5, 6. So here we go, about 1, 2, 3. Okay, there it goes. And then we, I probably need to extend that up a little bit. And then we do the same thing for this. We kind of cut this in half. And then we cut this one in half. Okay. Whoops. Something like that. That's not exact. Let me move this one up a little bit. Anyway, you would get something like this, where all three of these are perpendicular bisectors. And you notice for this obtuse, you're going to get an intersection out here outside the circle. So the point of concurrency is outside, not the circle, but the triangle. So the point of concurrency is outside for the obtuse, on one of the sides for the right, and inside the triangle for the acute. Now, if we're talking about the intersectors, or where these three lines intersect for the bisectors, the way we are here, not just any old three lines that intersect. We say that intersection, we call that intersection the circumcenter of the circle. Of the triangle. I keep saying circle. The circumcenter of the triangle. Now, we want to take note of some properties. When we do this, when we intersect all three of these sides, we get a point, the circumcenter of the triangle, and it has this property. The point of intersection here, the circumcenter, is going to be equal distant from each of the vertices of the triangle. Okay, so notice, so what we say is this right here is the same length as this, is the same length as this. Okay, that's what we want to take note about these perpendicular bisector intersections. Now, that's perpendicular bisectors of the side. We also want to talk about the angular bisectors. So here I've drawn a triangle, and I want to, approximately bisect each of these angles. So I'm just just looking at it. Okay, this is not exact. I'm not actually constructing it or anything, but it would go something like this. And notice we have an intersection here. Okay, so we have these three angular bisectors, and they all intersect here at a point. So this is the point of concurrency. Now, if we're talking about the point of concurrency for angular bisectors, we refer to that as the incenter of the triangle. So if we're talking about the point of intersection of the perpendicular bisectors of the sides, we call that the circumcenter. If we're talking about the point of intersection of the bisectors of the angles, we call that the incenter of the triangle. Both points of concurrency, but they have different names. Now, if we're talking about angular bisectors, then we say that the incenter of the circle is equal distant from each of the sides. So I've got a figure over here. Notice here's the point, here's the incenter of the circle. And what we're saying is the distance from that incenter to this side is the same as the distance from the incenter to this side over here, okay, which is the same as the distance here. So in other words, in this case right here, this triangle, PD is equal to PE, which is equal to PF. Okay. What we're taking note of in this section is points of concurrency. In the case of the angular bisectors, the points of concurrency is equal distant from the angles. In the case of the point of concurrency for angular bisectors, that's the incenter of the triangle, and those are equal distant. That point is equal distance from each side. So consider this triangle here. And notice that we have the incenter of the circle here, or the incenter of the triangle here. Now, what we know is that from this theorem, we know that this side, and this side all have the same length. So if we wanted to figure out, well, what is that length? Well, here's what we could do. Notice we know what this length is. It's given to us. It's 15. We know what this length is. It's 17. It's given to us. And notice this is a right triangle here, okay, because this is a perpendicular. So what we have is we have that 15 squared plus LQ squared equals 17 squared. So we can figure out what LQ is. LQ squared is equal to 17 squared minus 15 squared. And then we can just take the square root of that. And if we do, we get LQ is equal to 8. You may have recognized this is a 8, 15, 17 order. This is a Pythagorean triple. So when you see these sides together, it's like it's a real quick shortcut to getting the missing side. If you recognize that 8, 15, and 17 go together, it's like 3, 4, 5. Okay. Anyway, that's a side note. But there you go. Those are the two theorems that we need to focus in on for the assignment.